All right, so we started writing this this code last time. We had an Android project here, and I kind of mentioned that you didn't have to build any interface for this, just kind of prove that it was working initially. We'll start adding some interface elements. But if we go into main activity here, I went ahead inside of onCreate. I created an instance of our linked list, and then I told that guy to display himself, even though our display function currently doesn't do much, right? So back here inside of our linked list, here's our kind of default linked list where we have a node called head, and when we first create a linked list, head is pointed to null, so it doesn't equal anything. And what does display do? Display says, well, if we have if head is null, then print out empty list because there's nothing in that list. All right, so this program out of the gate should print out empty list. All right, so let's go ahead and test that here real quick. And then we'll look at adding front and that kind of jazz. Okay, available virtual devices. Let's use the Pixel. Why do they give you such small cups for post-chapel cup coffee? I mean, shouldn't they do better than this for free coffee? Really? I don't know. Why do they offer free coffee? I think is it like I think it's the university's way to like bribe you to go to chapel. Yeah, but only some people go in there, and they're usually like coffee hoarders, so they're not even really talking that much. They're just sitting there drinking coffee, like waking up. All right, so there's our hello world spit out there, which is just the default application. If we come in here and we click on, what is it, Logcat? There's our empty list right there. All right, so we got our basic linked list. This is what we ended class with last time. All right, so now we need to have the ability to add things to the front of our list. All right, and then we want to expand on display to test whether or not that worked, right? All right, so let's go back to our slides here and look at what does it mean to add something to the front of the list. We kind of did this last time. Let me just re-steal our stuff here. So I'm going to just move this over here. I'm going to point this here. All right, so assuming this is our existing list. All right, now in our case right now, our existing list is actually the empty list. So if we really want to mimic what we have exactly right now, oh no, I'll kind of drag that stuff out of the way too. So right now our list is this guy right here where head points to nothing. All right, so to add to the front of a list where head points to nothing, any way you cut it, we're going to have to create a new node. Right? Remember from last time, we looked at what's a node. A node keeps track of a payload, the value it's going to hold, as well as where its next node is. So what we want to do is we want to create this picture where we have a brand new node. We want head to point to that guy. Now, if head currently points nowhere, we come in here to add front. We ask the question, if this dot head is equal to null. If we currently have the empty list, then we want head to point to our new node. Now, any way we cut it, if we're going to add to the front, we're going to be creating a brand new node, right? If we go to our object for node, the constructor for node requires us to pass it a single payload, and he goes ahead and sets his payload equal to that, and then defaults next node to null. So the very first thing we'll do here is we'll go ahead and say node n is equal to new node and pass it the payload that was passed in. So no matter what the current state of the linked list is, we're always going to have to create a brand new node that we intend to add to our list. Make sense? Okay, so now we ask the question. So we're going to remember something. Remember, this goes back to 200. How do human beings solve problems? Memory, asking questions, repetition. So we're going to remember this node object that we want to do something with. Then we're going to ask a question. If our list is currently empty, which says if head is equal to null, then go ahead and set this.head equal to n. Make it point to the same thing that n points to. So we're going to draw that picture out here. We have a variable. I'm just going to steal this guy right here. We have a variable we just created called n, and n points to this brand new node we just generated. And here, just for the sake of cleanliness, let's just delete that other stuff. All right. So n points to this node right here, the node we just created. All right. Then we ask the question, if head is currently pointing to nowhere, which means we have an empty list, then we want head to point to the same place that n points to. Now, we made the comment in our code that we wrote was, we said head is equal to n. Yet I'm drawing a picture that says head is pointing to the same place that n is pointing to. When really I'm saying head gets the same value as n. What's the value of n? If we came in here to our code and I were to print out n right there, what would display? A memory address. So n's value is not a node. N's value is the location where a node lives in memory. That make sense? This goes back to that concept of if you're inviting me to your party, do you hand me the house or do you give me the address of the house? You would always give me the address, right? So n, because it's holding this node object, which might be this giant thing, isn't holding the node itself. It's holding a little piece of paper that tells us where we can go to find that node in memory. Okay? So n's value is a memory address. So what we're doing right here is we're setting head's value to be equal to n's value, which means we want head to hold the same memory address as n holds, which effectively means that they both now point to the same place. We've advertised this guy as being memory address 100. So if we kind of create that down here, I'll steal this here. If we say n is 100 and currently head was null, so that's what things currently look like. When I set head equal to the same value as n, head becomes 100, which means that it now points to the same place in memory. It has the same address as n has. So that's where we draw that picture to say it's pointing to that place in memory. Okay? If I have a little post-it note with my home address on it, and I hand Charlie a post-it note with my home address on it, we both can now get to my home address. We both have a pointer to my house. Plop it into the GPS and get there, right? Okay, so only if our list is empty do we set head equal to n, right off the bat. So that's the trivial case. Now what happens when this function ends? So right now, add front, we have this whole if head is equal to null, do this, else we're going to be doing the harder version of this, right, where we have to hook stuff up. Right? But when this function ends, what happens to n? Yeah, it gets garbage collected. It's gone. So during the run of the function, we have two different variables that point to this memory address right here. Right? So this guy has a pointer count of 2. Make sense? Now, when that function ends and n disappears, this guy now has a pointer count of 1. And that's okay. Only when it gets a pointer count of 0 does this guy get cleaned up by automatic garbage collection. The worst thing, kind of our the danger in any sort of linked data structure is that we accidentally lose track of some piece of memory and it gets garbage collected. So that's why we need to draw lots of pictures as we're writing this stuff, because we want to make sure that we hook pointers up in the right order so that we don't disconnect something that we can never then get back to. All right, so we've added one element to our list, no big deal. All right, so now let's assume that we're going to add another node. And we'll just assume this is at memory address 200, i.e. not contiguous. All right, and this is, well, it's going to be a 5, and this is, you know, in our mind, going to be, well, in our mind, actually, this is going to be the new bucket 0, and this will become bucket 1, right? Because we're adding it to the front. But realistically, we kind of can stop thinking about these buckets for a moment here. All right, so I have a new variable here called n. So this is n, and n happened to get memory address 200. So I just did this line right here. All right, I'm trying to add the payload 5 to my list, to the front of the list. That's what got passed into add front. So I create a new node out of the payload 5. I store, because we're using the new keyword, this is going to be generating a memory address. I'm going to store that address inside of n. And by our example here, that memory address is 200. Okay? Then we're going to ask the question. I'm going to stop printing it here. Is head currently equal to null? Is head pointing to nothing? Or does it point to something now? Points to something. So head is not equal to null. Head points to a real place. Therefore, we now need to write this else stuff. So what does this say? This says we are not dealing with the empty list. So we got to get fancy. All right. Now, we know that ultimately we want head to point to the same thing n points to, and then we want n to point to head. Now, if we're going to draw this picture completely accurately right now, when we build n, if you look at the constructor for node, we set the payload of that node equal to what was passed in, and then we set the next node equal to null. So it points out to nowhere. So here's our node. Payload is equal to the payload that was passed in. Next node is equal to null. That's what n is going to look like at this exact moment. Now, what happens if the very first thing we do, if we come into our code here, and we say, well, the first thing I'm going to do is I'm going to go ahead and I'm going to set head to point to n. So we know that's what it needs to point to in the end anyways, right? So if I say I want head to point to the same place that n points to, what did I just do? I lost this guy. He has a pointer count of 0. Can't get back to him. He's gone. So I can't do that first. The first thing I want to do is I want to take n and set his next node to point to the same thing that head points to. Make sense? I want n to point to the same place that head points to. So that means I need to set n's next node to be equal to head. Now if you go into node, notice that next node is a private variable. So I can't just come in here and say n dot next node is equal to this dot head. Why can't I say that? What does a private variable mean? Yeah, since it's private inside the node class, that means we can only access this variable inside the class named node. Right now, I'm inside of a class named linked list, which is not the same thing as the class named node, right? Therefore, I cannot access that private variable. How do I get around that? How do I give myself access to that private variable? Do what now? Getters and setters? Okay, now we could take the lazy programmer route and just make this guy public, or make this guy public, right? But we don't do that, we're good programmers. So assuming we're not going to do that, she suggested we use getters and setters. Now, at this point in time, we only need to set the next node. But now I promise you we're also going to need to be able to get the next node in the future. Okay, so what we're going to go ahead and we're going to generate a getter and a setter for next node. And then it probably makes sense for us to be able to get the payload. Payloads probably are not going to change. Sometimes kind of a cheaty way of dealing with linked lists is instead of reconnecting elements, you just change their payload. So the list already has its structure, and if you want these two guys to swap spaces, you just change the payloads between the two of them. Let's call that cheating. You don't want to do that, because there could be other things that get lost in memory depending on what the nature of your linked list is. All right, so we're going to go ahead and give ourselves getter and setter. Now remind me, what is a getter? When we say something is a getter, or the older, remember what the older term is for getter? Similarly, we have setters, and there's an older term for setters. They're accessors and mutators. Very, very old school. Nobody calls them that anymore. Everybody calls them getters and setters now. But what's a getter? A getter gives us access, read-only access to a private variable. All right. Now we can do the right-click thing and generate a getter and a setter, but I mean they're simple enough to write. So we're going to create a public function here. It's going to return if we're going to write, let's write the thing for payload first. We'll write the getter for payload. So it's going to return an int. We'll call it get payload. This guy requires no parameters in order to work. And we're just going to return this .payload. That's what a getter is, right? That's a public function, so we can call it from outside of this class, that returns the value, only the value, of a private member. So this gives us read-only access. It does not allow us to change it. Make sense? Similarly, we can say public node, because we want to do a getter for next node, get next node. Takes no parameters. This guy will return this dot next node. And then we can write public void set next node. And this guy's going to take in a parameter for the new node that we want it to point to. And we'll set this dot next node equal to n. So this gives us read-only access to our payload from outside of this class. This gives us read-only access to next node from outside of this class. And this gives us write access to next node from outside of this class. Make sense? Now, if this is how we intend to write it, especially for node here. So for next node, if we're going to give ourselves a getter and a setter just like that, could we have just made that variable public and had the exact same functionality? Because we're not doing any extra checking here, right? We're just saying, look, whatever you pass me, I'll set it to it. So really the rationale for a setter is for you to give some sort of wrapper in here and make sure that whatever they passed you is something that's reasonable to set that thing to. Does that make sense? So maybe we say that for set next node, we're not going to allow them to set it to null. Although, in actual linked list, we might want them to be able to set it to null. But the point is I've kind of made this argument that we should always make our variables private here, because that's good programming practice. But the reality here is that I forced myself to write two functions that whose functionality was already given to us had I just made that variable public. Does that make sense? So which is better? I'm going to still say make it private. Public gives us the convenience of this, right? But if you made this guy public, you would have instantaneously had read and write access to that variable. By making it private, at the very least, we had to consider Do I only need read-only access to it, or do I also need to be able to change it, and do I need to police the changing of this variable in some way? Now, maybe at this point right now, we can say, okay, I've gone through the motions. I've considered how I need to have access to this guy. Maybe now I can go ahead and scrap these and go ahead and make this guy public. But only after I've kind of been forced into the thought process of how I want this guy to work. Does that make sense? So if I make him public here, I can then go ahead and dump these two functions, because making that public gives me the identical functionality as these two functions. But I'm not doing it until after I've already gone through the motions, until I've already been forced into the thing that says, oh, I need access to the variable I previously did not provide myself access to. So I still always recommend starting variables off at private and then loosening the reins as it makes sense. So we'll go ahead and loosen the reins on this guy. Well, again, we could still make an argument. What's the negative? What's the downside right now of loosening the reins on this and making it public? It's not wrong. We can certainly do it. But we've introduced some inconsistencies now, right? Now, the way I access my payload is through a getter. The way I access my next node is just directly. So if I'm out here, if I make that guy public, notice that this guy now works. Make sense? But if I want to get the payload, I can't just directly access it. I have to get that guy through a function. So now I kind of have two different, I get my next node one way, and I get my payload a different way. Now, even though it makes sense why it's working that way because of the way I've written it, it might make sense for us to say the way we access all the members of the node class is the same. Kind of make sense? So if I were writing this, I would still keep this guy as private and then provide myself the getter and setter, even though the getter and setters aren't doing any extra security checking. Simply to provide myself a consistent way of accessing those members. But the point is that this is all personal preference. As a programmer, neither of those solutions are innately wrong. I just think we want to be as consistent as possible. That'll keep us from having screw-ups in the future. All right, so I'll keep it private. We'll give ourselves our getter and setter here. We gave ourselves a getter here. So now we're able to go back to our linked list. And I'm able to say n.setNextNode to this.head. So I can make n's next node point to the same place that head points to. That is, n's next node currently points to null. So I'm going to set his next node to point to the same place that head points to. Make sense? Then we can safely set head to point to the same thing that n points to, because I have not lost this memory now. So next line, head points to n. Make sense? So helpful to draw the pictures. Even though we had the exact same lines here, the order of those two lines was extremely important. Okay, so n's next node points to head, head points to n. The function then ends, n goes away. Have I added this brand new node to the front of my list? I have. Head points to that guy then points to the next node. Perfect. Now, one last little thing here. We're not quite done yet. So we had our picture before. This node also has a next node, correct? Let's say that I want to add another node. to my list. So currently the front of my list is here. I'm going to add this guy, so I'm going to add a 7 to the front of my list. I just happen to get memory address 300 for that, so this is N. And we said, oh, well, the first thing that we do is we make N's next node point to the front of the list. Right? Then we set head to point to N. Do we have to worry about this guy's next node? Does this list look correct at this point? It does. By drawing the picture with a more complex list, we've seen that, okay, we actually have hooked up all the things. One thing we're going to run into later on is we do need to consider whether or not we have an extra next node somewhere that we actually need to either disconnect from somebody, because what you don't want is to have this loop. You might have a situation where maybe this guy twists back onto this guy or something like that. So sometimes this specifically has to do with removing nodes from the list. You want to fully disconnect something, because you might now have 2 different pointers that point to the same object, even though one of them is disconnected from the list. Now that might not be something that ends up being a problem, but it makes sense to fully disconnect it. If you're doing plumbing at your house and you're changing out a pipe and you put the new pipe in, but you leave the old pipe connected, even though nothing is flowing to the old pipe, isn't that kind of weird? Right? You'd usually take that old pipe away because it's a useless pipe now, right? So I would say when you're writing linked data structures, you want to do the same thing. When you disconnect something from the list, fully disconnect it. And if you need to reconnect it at a later point in time, then reconnect it. Okay, so we're going to say we're good here. So adding to the front of the list is actually a pretty trivial task. So assuming we drew the pictures, right? A couple lines of code. Well, now we need to go back into our display. Decide, what does display look like? Well, display was really easy if head was equal to null. We just print out the empty list and move on with life. But if head is not equal to null, now we need to actually traverse the list. Right? So if head's not equal to null, we need to walk through our list, one node at a time, telling each node to display itself. Now we can do this a couple of different ways. We can do it from the level of linked list. So for instance, I can create a node, maybe cur node. So node, we call this guy cur node, and we'll start this off at head. So I can come in here, let's get N to go away here. And let me just move head up here so it's not crisscrossing our list so we can see it a little better. All right, so our list currently looks like this. So what I'm going to do is I'm going to create a second variable here called cur node. And I'm going to make cur node point to the same thing that head points to, because ultimately what I want to do is I want cur node to start off here. As long as he's not equal to null, print this guy. Then I want cur node to move to the next node. Move to the next node, so on and so forth. I need this second variable to do that because I don't want to break the front of the list. If I start moving head around, I've lost the front of my list. Make sense? So I need another variable to do this. So I'll make cur node point to the front. Okay. Then we'll say, so we're in the else now. So we know that if head was not equal to null, we know cur node currently points to a real place, right? And we want to keep doing this as long as cur node points to something that's not null. So does cur node point to something that's not null? Yeah, so print it. Then cur node equals his own next node. Does cur node point to something that's not null? Yes, print it. Then cur node equals his own next node. Does cur node equal, is cur node equal to something that's not null? Yes. Print it. Cur node equals his own next node. Does cur node point to something that's not null? No. So we're done. Make sense? How this guy's going to walk? So, while, now, how many times are we going to have to repeat this? We don't necessarily know, right? So a while loop lends itself to problems where we don't know how many times we're going to have to do something. We're just going to keep doing it until some condition has been met. So that's why we use a while loop. So we're going to say while cur node is not equal to null. Then what are we going to do? We're going to display the current payload. Whatever cur node is currently pointing to, we're going to display that guy's payload, maybe followed by a little arrow, kind of looking like a linky thing. So we'll go ahead and do a system.out. And I'm going to do a print. Okay, instead of a println, that way it doesn't kick it down to the next line. Actually, this is going to look, I wonder how Logcat's going to handle that. Let's look. Logcat might still put it onto the next line, but we'll see. So we'll do a system.out.print. And what are we going to print? We're going to print cur nodes.get payload. And I'm going to concatenate onto that a space, arrow, space. And that's all just for visual, just to look like a list. Okay? So as long as cur node is not equal to null, go ahead and print out his current payload and tack a little arrow on after it. And then we'll set cur node equal to cur node.get next node. So that makes cur node go down the list one. Then we loop back up. We ask the question, is cur node currently pointing to something? If yes, print out its payload. Move it to the next node. Over and over and over again until cur node finally points to nowhere. Finally gets a null because he set himself to his own next node, and the very last node in the list will have a next node of null. How do we know? Because when we first build a node, we default next node to null. So we've never set that guy's next node to something else. His default value is null. So what do we do at the very end there? Well, we'll fall out of this while loop, and we'll do a little system.out.println and just do the empty string or something like that. That'll finally kick it down a line. And we'll see what Logcat ends up making this guy look like. If it doesn't put it all on one line for us just because of the way Logcat works, then what we can do, well, let's assume it doesn't put it all on one line. It skips it onto multiple lines. But we wanted to have it all on one line because we're really picky for whatever reason. What would be an alternate approach to this instead of printing it out as we go? Say this again? Yeah, kind of build a string as we're going along and then do a final single print of that string we were building at the very end. Does that make sense? Okay, so let's go ahead and test this guy. We'll mimic what we have here. So we have, we started off with the empty list. Then we added 2 to the front, then 5 to the front, then 7 to the front. So we'll do ll.addFront2, ll.addFront5, ll.addFront7. It's very interesting that it does that. I think we saw that last semester. Yeah. Newer languages like well, Swift does it. Objective-C, which actually is an older language, has a syntax like this. In this case, this is not the syntax. It's just giving us a little helper thing, letting us know, kind of labeling what the 2 is. 2 is the payload we're passing in. This is not part of Java syntax. This is Android Studio kind of doing us a favor by labeling some stuff for us. All right, so we'll add 2 to the front, then we'll add 5 in front of that, then we'll add a 7 in front of that. So our list should look like 7 linked to a 5 linked to a 2. We'll go ahead and display that. So there's our 7 linked to a 5 linked to a 2. That make sense? All right, so that was the a solution to the homework assignment. Let's go ahead and let's do that string version of it, just to kind of practice some stuff. So we'll go in here, and instead of printing as we go along, we want to build up a string. So we'll go ahead and say string answer is equal to the empty string. Instead of printing something here, we're going to say answer is equal to answer concatenated with the payload concatenated with a arrow. Keep doing that over and over and over again. The very end, we'll print out answer. So rather than printing as we went along, we built a string as we went along and then finally printed out that string. Let's see that we get the same output in this case. I keep wanting to switch to a different application. Right there. Okay, so let's say then, well, first of all, we've seen that this works, correct? Let's say we weren't allowed to solve it that way. Is there an alternate solution you can come up with? What's recursion? Okay. And then last semester we dealt with some things I kind of said seems kind of like recursion when you're asking different objects to call the same function. Could we, if this is our list, could we ask this guy to display himself? And then have him then ask his neighbor to display himself. And then him ask his neighbor to display himself. And because this guy doesn't have a neighbor, he's done. So rather than doing it the list side of things, so at this point I'm linked list. Okay, at this point I'm linked list, and I'm looking down at my entire linked list, even though I really only have a starting point here with head. I don't know what's farther down the list. Because I have the starting point, I can traverse this list with kernode. Right? I can start here and then have kernode walk from element to element to element. But if I didn't want to solve it that way, if I wanted to use a more recursive approach, so I'm going to go ahead and I'm just going to comment this out so it's still in there in the solution. And instead what I'm going to do, now if I'm in this else, I know for a fact that head is an actual node, right? Because I'm in the else to this if. If head is equal to null, we printed out the empty list, we're done. So if I'm in the else, I know that head points to a real node. So what I'm going to do is I'm going to go into node, and we're going to write a public function called display. We're going to teach a node how to display itself. So when a node displays itself, what does it do? Well, it's going to say system.out.print this.payload concatenated with space arrow space. So that's how a node displays itself. But then we're going to ask a question. He's going to say, do I have a neighbor? How does a node ask if he has a neighbor? Yeah, he wants to know if his next node has something in it. So if this dot next node is not equal to null, if I have a neighbor, then I'm going to tell my neighbor to display himself. This dot next node dot display. That makes sense? So this looks a lot like a recursive call because we are calling nodes display method, but it's not the same node. It's the next node's display method we're calling. Now, if he didn't have a neighbor, the last thing we see out there is just this one extra little arrow. That makes sense? Now, if we wanted to look identical to what we had before, what we would do is we would print out just the payload here, and then if he has a neighbor, we would say system.out.print space arrow space, and then tell his neighbor to display. So we would only throw that extra arrow there if we have a neighbor. Because remember in our previous thing, oh no, we did write it to have an extra arrow there at the very end. So my original solution was better. I originally thought we didn't have one extra arrow there at the end. That was just the end. So since we did have an extra arrow there, we can take this out and put it back there. So the very last node will print out his payload, followed by an arrow. Then he'll notice he has no neighbor, and we're done. That makes sense? So then inside of linked list, in order to get the ball rolling, what do? I've built all the logic into node. Yeah, just tell head to display himself. So in linked list, I'll say this dot head dot display. So that's the entire implementation in linked list. You tell head to display himself. He's a node. So what does head do? He displays himself. Then he says, do I have a neighbor? If yes, ask my neighbor to display himself. The neighbor displays himself. Then he asks, does he have a neighbor? If yes, tell him to display himself. So on and so forth until he runs out of neighbors. Make sense? Where's my output? Let me run it once more. Definitely should have an output. Am I just missing it? Does anybody else see it? Well, verbose shows everything. Oh, you know what I bet? I bet. Just because of the way Logcat works. You got a system.out.println. Everything gets put into this buffer, and then you need, when you do a println, it actually clears the buffer. I bet you this will tell us whether or not that's how it works. So let's just look here real quick. Yeah, there it is. So what ends up happening is every single time you do a print with Logcat, which isn't a big deal for us because typically with an Android app, you're not using Logcat. That's just for our little debugging, right? But when you do a print instead of a println, it's kind of loading something into a queue, but not actually spitting it out to the screen. And only when we finally did the println did it kind of flush that pipe to get the stuff out to the screen. That makes sense? Again, not a big deal. That's not a Java thing. That just happens to be the way the Logcat tool works. But we see we got the same output. So now, the reason I did it this last way, well, first of all, do you have a preference? Which of those do you like better? Okay, so let's look at it a couple different ways. For most of you, the first way would have been the one that was easier to understand, right? Because it's all kind of laid out in front of you. It's like, oh yeah, we just hop from here to here to here to here. The second we kind of turn over the wheel to our individual objects and let them kind of take control, it kind of goes under the hood and some of the magic is hidden from us, even though the logic, once we explain it out loud, maybe makes sense. To conceive of that idea is a little bit harder at first. And that has nothing to do with your intelligence. It has more to do with, up to this point, we've dealt with primarily procedural programming. Even though Java, if you go way back to 200, we started talking about different kinds of programming languages. One of those slides, there's 3 kinds of programming languages: functional, procedural, and object-oriented. Those guys, we kind of said, don't worry about functional. You'll deal with that in 470 when you take that. But even though we're using an object-oriented language like Java, most of what we've done, even though we've been using some objects here and there, our problem-solving approach has mostly been linear, has mostly been procedural. Do this, then this, then this, then this, then this. So we're most comfortable with seeing solutions that are just laid out in front of us. When we have to start turning over control, where we're kind of delegating. We're saying, you go and do this, you go and do this, you go and do this. That's outside of our comfort zone from a problem-solving perspective. Now, you mentioned, and obviously you've had some programming before, so it's, you're maybe ahead of the curve. So you mentioned that you think it's cleaner. Well, clearly it is. If we look at Node itself, this is pretty simple logic, right? From a Node's perspective, it's like, look, I'll print myself, and if I have a neighbor, I'll ask him to print himself. That makes perfect sense. I'll do my thing, and I'll tap him on the shoulder if he's there. If he's not, I won't. And then back here, all we're in charge of is the top of the list, the very beginning of the list. And what will we say? We'll just say, okay, first guy. He's the only one I know about. I'm the linked list. Okay, here's the guy that's in the front of the line. Everybody else is behind the black curtain. Okay, there might not be anybody back there, but I don't know about him. All I know about is this first guy, so I'll tap him on the shoulder and say, you, display yourself. That all makes perfect sense, but to conceive of that solution first, might be a little bit of a reach for us right now, because that's not the way we're used to solving problems. Okay, but the reason I wanted to show you that to you is because we're going to quickly start stumbling upon things where this kind of approach will make more sense, will make life easier than a more linear approach. But that doesn't mean it's better than a linear approach. In fact, more often than not, recursive approaches are somewhat dangerous, even though this isn't exactly a recursive approach, since it's technically different node objects that happen to be calling their display method rather than the same function being called over and over again. What's the downside to recursion? Why can recursion be bad sometimes? Well, definitely an infinite recursion is horrible. Okay, but why is it horrible? What does recursion take a lot of? It takes a lot of memory. Okay, and we go back to, you can think back to the 200 class when we were talking about kind of the, different kinds of programming languages and looking at like the size of variables, and we talked about, like why are there so many different ways of storing signed integers in Java? Remember that? If we look at our primitive types, what we have byte, short, int, long. So 4 different ways of holding the same kind of values. Well, why do we have that? Why do we have 4 different ways of holding whole integers, whole signed integers, positive and negative numbers? Don't we just need one? Why do we have 4 ways? Memory used to be really expensive. And these primitive types that we have in Java really came from what? We look up the family tree. See, we got an older language way up there. We have C++ before us, and then C before them. And those primitive types have just been handed down. So back then, in the late 70s, let's say, late 60s, even 68, I think was the year C came out. Ballparky, I might be losing it a little bit, but I think it's right around then. Memory was really, really expensive. Whereas a programmer, we had to pay a lot of attention to how much memory we used. Never use more than you actually need because you're working with a very limited resource. That's not the way we solve problems today. Our modern programmers treat memory as an infinite bucket. And it's fine. I mean, every now and then you'll run into a problem where memory, you do have to consider memory. These really large problems that are buffering a whole bunch of graphics or something like that. But generally speaking, memory is inexpensive today and we have a whole lot of it. Right? So today, you would probably never see somebody use a short primitive type. Okay, the short primitive type is, if you remember from Java, is the 16-bit signed integer versus 32-bit for an int versus 64-bit for a long. So you would pretty much never see anybody use a short. You still might see somebody using bytes, which is an 8-bit number. Why might you see somebody using bytes? Go ahead.
They work well for like RGB stuff because you can have 255 for red, green, and blue.
Except you can't put 255 in a byte. Bytes assigned value. Negative 127 to positive 128. But that's not necessarily an inaccurate answer. But it's probably the not really the correct answer for it, because I mean, most people who are going to do, if they're doing RGB stuff, we're not talking about heavy memory stuff. They'll just toss it in an int and move on with life, right? Int can hold 255. Just thumbs up and move forward. We do a lot of video streaming, things like that. Well, when you're streaming stuff, when we talk about network activity, things travel across networks in bytes or chunks of bytes. So it's kind of the right size shoebox that we're throwing down the network anyway. So if we're receiving it in bytes, we might as well put it into a byte. It's the convenient size packaging, not because we're really trying to save memory. Does that make sense? So that has more to do with, I think, a lot of video streaming type stuff, or network programming where we're digesting things 1 byte at a time for serial type networking stuff. Very little to do with memory itself. Okay, so questions about any of that stuff? We're starting to get a feel a little bit for the pointer hookup stuff and things like that. So we're ready to do something actually more difficult now. This was too trivial, right? It can't be as hard as it gets. Okay. So what if I have this linked list and I want to add something to the end? So we'll go ahead and create another node. And we'll stick with our cadence, and this guy happens to be at memory address 400, and we're going to try to add a 9. And I don't want to add this guy to the front of the list. I want to add him to the end of the list. So I want to add him down here. And just for completeness, remember this very last node here has a next node that's currently pointing nowhere. How would you go about doing this? Forget about the programming side of things. Just, we got a little puzzle sitting in front of us, and we want to get this guy inserted onto the end of this list. That is, he is after this node right here. Go ahead.
Traverse node.
Okay, so when we get to a next node that's equal to null, what does that mean? Yeah, we're at the end of the list. So we go here, says, so we started head. We said, does this guy have a next node equal to null? No, he's got a real neighbor. So we go to him. Does this guy have a next node equal to null? No, he has a neighbor. So we go to him. Does this guy have a next node equal to null? Yep. End of the line. What do? We hook them up. Okay, so how do we traverse that list then? What pattern have we seen today that allows us to kind of traverse through a list? We had that cur node thing when we used it for, so we can create another variable here. Maybe called cur node. And we'll start it off pointing to the same place as head points to. And we're going to have cur node jump from node to node to node until it finally reaches something where its next node is null. Make sense? We'll go into linked list. After add front, we'll put in an add end. This guy will take in a payload. Now, rather than reinventing some of the wheel, if head is equal to null, what could we do? We just add it to the front. We already have the logic for adding something to the empty list. So we could just ask a quick question. If this dot head is equal to null, if I'm dealing with the empty list, the front and the end are the same. So we'll go ahead and just say this dot add front and pass the payload over there and let him do the work. We already wrote that. Now, again, it was only like one line of code up there, so we probably could have just done it here, no big deal. But one of the goals of object-oriented programming is not to repeat code. You reuse as many of your resources as possible. So this is probably a coin flip as to whether or not you're going to write this one line of code or write that one line of code. But at least this gets us into that mindset of relying on things we've already written that already solved. Don't resolve a problem we've already solved. Okay, so if I'm dealing with the empty list, let's just use our add front to add that guy to the front of the empty list. Else, if I'm here, I am not using an empty list. I'm not working with an empty list. Therefore, I need to traverse to the end of the list and then tack on my new guy after that. So I'm going to need my variable n. So I'll go ahead and generate a new node there in terms of the payload that was passed in. Okay? So this guy has the payload. His next node's pointing to null. He's just sitting out there ready to be placed somewhere in the puzzle. Then we're going to go ahead and we're going to create our node cur node and start this guy off at head. So we'll have him pointing at the front of the list. And as long as he has a next node, we want to move him. So originally he goes here. Does cur node have a next node? Yep. So set cur node equal to his own next node and ask the question again. Does cur node have a next node? Yep. Set cur node equal to his own next node. Ask the question again. Does cur node have a next node? No. You want the loop to end. So we're going to have a while loop that's going to keep doing something as long as cur node has a next node. While cur node dot get next node is something other than null. That says cur node has a next node. If cur node has a next node, what are we going to do with it? We're going to set cur node equal to his own next node. Update his memory address to point to the next guy's memory address. So this will make cur node do something like this. He'll start here, then he'll update his value to point to his own next node, Then he'll update his value to point to his own next node. And finally, he recognizes that he doesn't have a next node, because his next node is equal to null. And what happens here when cur node's get next node is equal to null? Well, just simply speaking, what happens to this while loop when that condition is true? It ends. While loop's over, which means that we get dumped out right here. Oop. It's really over. We get dumped out right here. And if we're right here, what do we know? We know cur node is sitting at the last node. It's sitting at the node whose next node is null. Make sense? And then at that point, as you were pointing out, that's when we add it. So if I'm sitting like this and I have cur node pointing here, how do I add this guy to the list? So I got n sitting right here, ready to be put in the list. Okay, we're going to set cur node's next node to point here, right? So we want to set cur node's next node equal to n. Cur node dot set next node to n. Go ahead.
Is there another way that you can write your while loop embedded? Like, could you just say like not near cur node dot get next node?
You actually can do that. It's something I typically don't introduce, but actually, I'm pretty certain you can definitely do that in C and C++. I'm pretty sure you can do it in Java. What she's saying is, can you do this? Can you say while not cur node dot get next node? You can't do it in this language. Typically, null in a lot of programming languages boils down to false. So in this one, it doesn't. So you can't write it this way. But in a C or a C++ implementation, saying not cur node dot get node is the same thing as saying cur node dot get next node not equal to null. So little trivia thing, put that away somewhere, because in C and C++, you can see that. And you're going to see it in 450, that we will test Booleans against null values. Okay, so this just takes us on that voyage to the end of the list. If you can come up with another way to get to the end of the list, that's fine. But at the end of the day, what do we need to do? We got to get to the end of the list. And at that point, we tack the new guy on. Okay? So this will add him to the end of the list. Once we've tacked him on, do I need to do anything special? Do I need to update n at all? Or can I go ahead and just let the function end? N then disappears. I'll go ahead and leave n0 here so we can repurpose it for this guy's next node. So our list will look like that. Cur node disappears, and now our list has this new guy added at the very end. Go ahead.
Delete that other arrow off of the 100.
Where'd that guy come from?
When you were trying to show that.
Oh, going backwards would be a problem. Yeah, so that's what the guy should look like. All right, so let's test that. Let's go ahead and tack a 9 onto the end of the list. Then when we print it out, we should get a 7, a 5, a 2, and then a 9, if it's stuff's getting added correctly. So we'll go into main activity. We'll say ll.addEnd 9, and then we'll display it. It should be 7529, should be our output. 7529. Right there. Make sense? Okay, so now, what about implementing the add end in a similar way to how we implemented display in kind of our recursive-ish? Didn't I come up with a name for that last semester? Was it recursive-ish? Was it a... Sounds like something I would say. Because it's not technically recursion. It's not a function calling itself. It's a function calling its like first cousin, you know, because it's technically a different node. But regardless, we'll call it recursive-ish. So our recursive-ish solution that we use for display, could we implement add end using that, an approach similar to that? If we look at our picture here, to add something to the end of the list requires us to find the end of the list, right? One way or another, we need to get to the end of the list. That's what's important. So the way we approached it is we said, we're just going to start a pointer off at the same place as head, and we're just going to keep moving that guy until he's pointing at the end of the list. Does a node in and of itself know if he's at the end of the list? If you're a node, how do you know that you're the end of the list? Yeah, you got no friends, right? No neighbor. You say, who's my next node? No, nobody's sitting at the lunch table with me, right? So we can ask a node to tell us if he's the last node, right? Could we then ask our nodes to go ahead and add to the end? Just keep passing our payload through. So can I come in here and do something like this? We'll add it up here right before display. We'll say public void add end. We'll have this guy take in a payload. And he's going to do one of two things. He's either going to build a new node and set his next node equal to it, or he's going to ask his neighbor to do to call his add end method. If this dot next node is equal to null. If I don't have a neighbor, then I'll say this dot next node is equal to a new node built with payload. Right? Else, I got a buddy. So if I have a buddy, what am I going to do? I'm going to tell him to add it to the end. I've done all I can. So I'll say this dot next node dot add end payload. That make sense? So then I can come in here to link list. And instead of all of this crap, I can just do that. I can tell head to add to the end. Okay, so if she's the front of the list, I'm going to tell her to add to the end. She's got a buddy, so she's going to pass it to you. You're going to say add to the end. You have a buddy. She's going to say, I'm going to add to the end. You have a buddy. You have a buddy. You have a buddy. Ah, Charlie, you're into the list. No buddies. The way the chips fell, man. All right, so this works too. Go ahead and run it again. We'll see that we have the same output. Here's our list, 7529. Which do you like better? Is it? Yeah, so yes, it's shorter. Maybe not by time, because the first thing wasn't horrible, but it is shorter. Does shorter mean simpler?
No. But when practice, yeah. But
Well, and that's the thing. That's kind of why I'm showing the two different implementations here. I would say that adding something to the end. Well, okay, so let's think about what we've learned today then. If you can conceive of this solution, I mean, once I spit it out there, it's not that bad, right? But that might not be the way you initially think about it, just because of the way we've been solving problems. So kind of drilling that idea home. So we've seen two, I mean, we would call those two pretty different approaches that come out with the exact same solution, right? Is one really substantially better or worse than the other? I mean, if we sat down and really broke it apart, maybe one uses a little bit more memory than the other, or maybe one has to do a couple of extra comparisons. But given how fast our computers are and how much memory we have, they're the same. We'll just call them the same. So which should you use?
I would use this one.
Because it makes you feel cool?
No, it's just makes gets sense better, sense less step, you know.
Whatever makes sense to you.
Okay. I mean, I think that's certainly an easy enough answer to say whatever makes the most sense to you. Certainly, come up with the answer that you can do correctly, rather than the cool kid way that you can't get right. So that's definitely the deal. Could we have done it the recursive-ish way for add front? Well, not just pointless. It actually really wouldn't work. So now we have this issue of consistency. Kind of back to the same thing we talked about earlier with the private. You know, why should I make this one field public when the other guy's still private, just because technically my getters and setters weren't doing anything special? Is there something to be said for your solutions to all be somewhat, consistent with each other? If you're taking the linked list approach of, at the linked list level, I'm going to traverse my list to get myself into position, and then I'm going to tack something in there, even if it makes less sense to you or it's a toss-up or whatever, if that's kind of the way you're doing it on a consistent basis, might it be best to keep your solutions similar to each other so somebody who's looking at your code later on can kind of, they know the way you're thinking through these problems? Kind of makes some sense? So we're adding a little bit more variability into our solutions here where, anymore it's not even about what's the best solution or the worst solution. Sometimes there's something to be said for who might be looking at your code later. That's where comments come in. That's where, maybe writing something in an easier to understand way rather than the most efficient way maybe makes some sense for, let's call it, most problems. Because you might not be the one who's always looking at your code. Okay, so homework, I'll go ahead and push this. Homework for next class is to now add an interface to this that allows you to put in some text in a text box, a number, and then you have a button either add front or add end. All right, and depending on which of those guys you click, you're going to show a list of text views. And it'll either show it at the front of it or the end of it, so you'll have this ongoing list. So remember from last semester, we had a scroll view with a bunch of text views we added into it with view groups. Remember view groups? So we're creating an interface for this guy. So this will kind of get you back up to speed building your interfaces. So you're not going to have to do any more linked list stuff for next class. You're just going to be calling our current linked list stuff for you having a front interface. So give yourself a text box, have a button for add front, add end, and then have a way of showing your list at the bottom. I would suggest you have a scroll view, which a bunch of text views inside of it. When you add something to the front, the new text view shows up at the top. When you add something at the end, the text view shows up at the bottom. Make sense? All right, I will see everybody on, today's Thursday, right? I'll see you on Tuesday. Who? What? Yeah, Bible homework's due by midnight tomorrow. Yeah, it's been up, right? It's on. I didn't say it last class? Oh, yeah, it's shorter though. This semester, the Bible homework each week is like 1 to 2 paragraphs. So, this should not be this should be free homework points that's forcing you to read the Bible. Capiche? All right.